Okay, so we're going to enter into the solar system and look at our solar system for astronomy, but one place to start is our own Earth. Earth is part of the solar system, and to understand astronomy better, we need to understand what's happening to the Earth. And in particular, the Earth and its moon. Here's a depiction of the moon and the Earth as given by Van Gogh. Very pretty picture called Starry Night. Here's another one by Van Gogh showing the moon setting and a field. Recently, some scientists have thought that they have discovered where this landscape actually was. So that's kind of interesting. If we focus in on this picture of the moon, we can actually see a picture of the real moon as seen from Earth and a depiction of the Earth's, or a picture of the Earth's atmosphere near the surface of the Earth itself. Here's a look down on the Earth from the first commercial spacecraft in space, Spaceship One, from a few years ago. And this picture was taken from 70 miles up. Officially, if you go 63 miles up, you are in space. So this is from 70 miles up, and definitely you can see the curvature of Earth. You're way above the clouds, and you are in space. Earth's radius is 4,000 miles, so if you only go 70 miles up, you're only going a fraction compared to Earth's radius. So it tells you that you don't have to go very far above the Earth's surface to reach space. Here's another look at Earth. This particular look at Earth is from the Smart 1 spacecraft. And what we're looking at here is Europe. Appears that you're seeing the coast of France right here, and this might be Africa down here, and the Straits of Gibraltar right there. So here's Spain and the Mediterranean Sea. So you're looking at Europe. The Smart 1 spacecraft was a spacecraft that is going through many orbits, increasing orbits around the Earth using an ion engine. And its purpose is to look for the possibility of Earth-Moon debris from the formation of the Moon from the Earth 4.6 billion years ago. So the Smart 1 spacecraft is slowly making its way to the Moon. Here's another picture of the Earth in the background. Be a better picture if this astronaut didn't get in the way, but you know how astronauts are. They always want to get in the picture. So the astronauts got in front of this nice picture of Earth. Looks like New Zealand right there. One way to look at Earth is from outside of Earth, and as you're looking down, you might see some weird things. Here's the Nazca Plain in Peru, and there are some images of some definite images of creatures on Earth that can only be seen from the sky. And so some theories are that these images were set there for to establish landing pads for ancient astronauts. But another theory is that in these cultures, they actually had developed good enough textiles to actually form hot air balloons, and that in this culture they actually had the ability to fly around in hot air balloons, and hence they'd be able to see these images from there. If this truly was landing airports for extraterrestrials, then probably better would have been to put out a neon sign like the Saturn drive-in so that the extraterrestrials could land and pick up a good burger and root beer float or something on their way to somewhere else in the solar system. Here's a picture, 1967, Earth from space, and I never tire of looking at these pictures of the Earth from space. Just such a beautiful world. And looking at this, you can start seeing some of the contours of, say, South America that might fit into the contour of Africa over here. Here's a more recent picture and higher resolution picture of Africa, and you can see Madagascar here, how it would fit right into that little section of Africa right there. And you have Antarctica down below here. Here's a picture from space showing populated areas and light coming from around the world. Here's a picture of the MIR spacecraft in orbit around the Earth, and of course the MIR is interesting, but most interesting, I think, in this photograph is the picture of the Earth, and you see the curvature of the Earth, and you see the Earth's atmosphere right here. It's just this thin blue line is the Earth's atmosphere, and you get a picture of how thin that atmosphere is. You know, we think about the wide sky, the blue sky above us, and how endless it seems to us as we're on Earth. But truly, in the sense of Earth, it's just a real thin layer of gas that is surrounding this large planet. And hence, it's something to be concerned with for the fact that it is not limitless. It's actually quite thin and small, if you will. Here's another look at the atmosphere. Here, greatly exaggerated to show us its features. We have closest to the Earth the troposphere, up to about 10 kilometers in height above the surface of the Earth. Then you have the stratosphere for another 40 kilometers or so. The mesosphere, the site of the ionosphere, and the thermosphere, where the temperature increases rapidly. And the atmosphere can be even thought to go beyond that, beyond 400 kilometers in the exosphere. 80% of the atmosphere is actually contained in the troposphere, closest to the Earth, and as it thins out, most of the rest of the atmosphere, just about 20% of it, is in the stratosphere. So you have almost exactly 100% of the atmosphere in these two smallest layers within 50 kilometers or about 30 miles of the surface of the Earth, and then less than 1% of the atmosphere above that. Here's another look at the atmosphere. Of particular importance are several layers that are in our atmosphere. In the ionosphere, we have which is part of the mesosphere, we have the magnetosphere. And the magnetosphere holds the Earth's magnetic field, which is a very good layer because it protects us from the charged particles coming from the universe and from the sun. And without that magnetosphere, we would not have life as we know it, because we would be burned by those charged particles. We have the ozone layer, which is right at the top of the stratosphere, and it's kind of a layer in between the stratosphere and the mesosphere. In the ozone layer contains a lot of ozone, which absorbs ultraviolet radiation. And in fact, it absorbs about 99% of the ultraviolet radiation incident on the Earth. So without that layer, we would not have life as we know it on the Earth. We would be burned by this high radiation, this ultraviolet radiation. We have the site of our weather in the troposphere, around this cloud layer, and if we think of it, the troposphere is containing a lot of the carbon dioxide and water vapor in the atmosphere, which helps hold in the infrared radiation that heats up the Earth. And so without this layer of gas, life as we know it would not exist, because we wouldn't have the temperate conditions that are needed for life as we know it. So we have these three layers that are absolutely essential to life as we know it on Earth: the magnetosphere, the ozone, and the troposphere containing different gases that hold infrared radiation in. And at the lowest level, right on the surface of the Earth, we have life as we know it. Just about 99% of those two elements. And then another 1% contains a bunch of different gases, including argon, carbon dioxide, and water vapor. Carbon dioxide and water vapor being particularly variant, water vapor in real particular. So those can change their percentages. But mainly 21% oxygen, 78% nitrogen. And I've been told in the past that if we had more oxygen, that would not be good, because certain conditions would cause more fires to ignite because of the higher level of oxygen. And if we had lower than 21% of oxygen, that wouldn't be good, because life as we know it would not exist. The kinds of life that we see depends on having just the right level of oxygen present. So the conditions of this air are just perfect for life as we know it, to have 21% oxygen in not an inert atmosphere of nitrogen, but in an atmosphere of mainly nitrogen. No light gases like hydrogen and helium, because Earth's gravity is too weak and Earth's atmosphere is too warm. So it's for those light elements under this temperature that we have, they have too much velocity with their kinetic energy, and with that velocity they escape Earth's gravity. So in our atmosphere there is no hydrogen and helium. We have to get hydrogen mainly from water, and helium is trapped in other ways. The oxygen is originated by plant life through photosynthesis, and so we have this interaction between plant life and breathing carbon dioxide and giving off oxygen, and animal life breathing oxygen and giving off carbon dioxide. So look again, another nice look at Earth. Like Venus and Mars, Earth once had a carbon dioxide-rich atmosphere, predominantly carbon dioxide. But the oceans dissolve a lot of that CO2, and in the past, the oceans would dissolve the CO2, and it was deposited as limestone, as calcium carbonate. So there's a lot of limestone around the Earth, and if this particular limestone, if all the CO2 in this limestone were released from centuries past, Earth would actually be 98% carbon dioxide and only 2% nitrogen. That 78% nitrogen would only comprise 2% of this new atmosphere, which would be 98% carbon dioxide and 70 atmospheres of pressure. So we would be predominantly carbon dioxide, and we would have a much thicker atmosphere, very similar to the kind of atmosphere that exists on Venus. Because of the carbon dioxide that is in our atmosphere, we have the greenhouse effect, and the greenhouse effect is actually a very good thing for life as we know it. This is how it works. We have sunlight coming in, either in the form of visible or maybe possibly some ultraviolet, coming in, heating the ambient world, and then that's re-radiated. But when it is re-radiated, it's at longer wavelength infrared radiation, which gets trapped by the gases in the atmosphere. So essentially, it's kind of like a greenhouse, because we have, in a greenhouse, you would have sunlight easily making it through the window panes, heating the ambient environment inside. And as that environment re-radiates energy, it re-radiates it at lesser energy called infrared, which gets trapped by those same window panes. So that heat is trapped in, creating a warmer environment. And this is what happens with the Earth's atmosphere. So the gases in the Earth's atmosphere trap this infrared heat, the long wavelength. Some of the, if you heat it up too much, some of that radiation would escape through as being shorter wavelength, higher energy radiation. So that would be one mitigating effect if we were to heat up too much. So the question is, since this is such a good effect, this warming effect, is it possible that the Earth is warming too much? Well, with any kind of scientific problem, it's always nice to look at extreme effects of that problem. It kind of puts things in perspective. So one way to look at this is to look at other planets that are near the Earth. For instance, let's look at Mars. Mars has a predominantly carbon dioxide atmosphere, 95% carbon dioxide to 97%. But its atmosphere is much thinner than ours. It's about 150th of the thickness of the Earth's atmosphere. So even though it's predominantly carbon dioxide, it's not very much. And hence, it really doesn't have much of a greenhouse effect, or not enough of a greenhouse effect to maintain the kind of life that we see on Earth. At one time, Mars had a much more significant, much thicker atmosphere, and it's believed that half of its surface was covered with water at that time. So it had more of an atmosphere, warmer temperatures. It could sustain liquid water for some time, but over the years, millions of years, billions of years, its gravity could not hold that atmosphere, and it's too far away from the sun to maintain heat enough, so it lost most of that atmosphere, most of that carbon dioxide. So the result is, with too little of carbon dioxide, it has a small greenhouse effect, and Mars is cold. On the other side of the coin, there's Venus. Venus is 0.7 astronomical units away from the Sun, so it's still far enough away from the Sun. It's 70% away from the Sun, as we are. Being that much closer to the Sun, it receives twice as much insolation as we do. But that does not account necessarily for how hot it is, which is 900 degrees Fahrenheit. And that's because it does have a predominantly carbon dioxide atmosphere, 95% carbon dioxide, but it's 90 atmospheres of pressure of that gas. So any radiation coming in is totally being trapped by this atmosphere, and hence it's heating up the planet. And even though it's much further away from the Sun than Mercury, Venus is the hottest planet in the solar system at 900 degrees Fahrenheit. So it basically is a greenhouse disaster. And those conditions that we explained with 90 atmospheres of pressure and predominantly carbon dioxide were the conditions that once existed at some time on Earth. And as we said, the oceans and oceans help mitigate that by dissolving that carbon dioxide and transferring it into calcium carbonate or limestone. So the Earth is just right. the greenhouse effect on the Earth is just right, like Goldilocks. Earth is warm enough, not too warm, not too cold, not too hot, just right, just enough effect, just far enough away, just enough atmosphere to maintain temperate temperatures, to maintain liquid water on its surface, perfect for life as we know it. Now, when we're talking about these conditions, that Earth being the perfect conditions, the Goldilocks planet, where everything's just right, well then if you have those kind of conditions, you don't want to disrupt them too much, because if everything is just right, it's a balance that's there that if you push it one way or the other, you push it out of that just right zone. And we can see what's happened to Mars and Venus. And here's something of possible concern. Here are the global annual mean temperatures over the last 50 years of the last century. I don't know why we don't look at the global annual nice temperatures over the last century. But we can see that in many places on the Earth, they have been getting hotter, up to 5 degrees centigrade hotter. Some places are getting colder, but if you take the globe as a whole, on the average, the global temperatures are getting warmer. Here's the degrees centigrade change over the last 120 years, at least between about 1880 to around 2000, using the average value for that range in comparison. And we see in the 1880s, everything was below that average, and in the 1980s and beyond, everything was above that average. And in fact, up to 2002, when I first made this chart, the top 5 hottest years on record were just prior to 2002, at least within that last dozen years before 2002. So 1998 was the hottest year on record. 2002 was the second hottest on record. 2001 the third hottest, and so forth. So those were the 5 hottest years on record just prior to 2002. If we look at the next 5, those are just prior to 2002. So we have 6 through 10. And if we look at the next 5, those are just prior to 2002. We do have one anomaly down in 1983, year 13, but most of the top 15 years are just prior to that 2002. We also have another anomaly here in 1992 and 1993, which were cooler, and there's a reason for that, a cooling effect, so it helped to mitigate the global warming temperatures in those 2 years. But even with that mitigating effect, those were still years 16 and 17 hottest years just prior to 2002. So 16 of the hottest 17 years on record were immediately prior to the year 2003. Well, I updated this in 2005 and found that 4 of the hottest years on records were just prior to 2005, including 2005. So up to that point, 19 of the last 20 years were the hottest years on record. The last 4 years being in the top 5. Well, as I'm recording this, this is 2009. And as we look beyond 2005, 2007 came in here as second. 2006 is coming in here, and 2008 coming in here just around a tie for what would now be 5th. But they are in the hottest years on record. Actually, you have a slight dip from the hottest in the last couple of years, and that might be attributed to a lessening of solar activity. We're in a solar lull here between those 11 years of solar cycles. But I'm told that now we're headed to another maximum to occur in 2012. So from 2008, it's expected with this slight variation to solar activity, we might be headed to even warmer temperatures. Here's an excellent graph to illustrate all these effects. We have the average temperature here indicated by this red line. We have the blue line indicating carbon dioxide concentrations in the atmosphere. So there seems to be a definite correlation scientifically between carbon dioxide concentrations and the warming trend of climate change. We also have solar activity on the bottom here, and we can see slight bumps in this change in temperature anomaly due to solar activity. So as the solar activity increases between 2009 and 2012, we might expect to see more problems towards the top of this curve here. The hottest years on record are towards the end of this time period from around 1850 to 2010. We are now in the hottest time period on record. Key to this, though, is climate change. We have this delicate balance of just right conditions, and as this balance is disrupted, we don't know where we're headed. One of the other layers that protects life as we know it is the ozone layer at the top of the stratosphere. The ozone layer blocks 99% of the harmful ultraviolet radiation, and in recent years, ozone hole has been observed to form over the Antarctica and over the Arctic, which allows more of this ultraviolet radiation through. Just think about this. You go out and protect yourself with sunscreen, SPF 45, say, to protect yourself from ultraviolet radiation. That radiation that you're protecting yourself with is that 1% that actually makes it through the ozone layer. So, ozone layer blocking 99% of that radiation from the sun. So what would happen if instead of blocking 99% of radiation from the sun, the ozone layer blocked only, say, 98% of the radiation from the sun, blocked just a little bit less? Well, that UV radiation that you're exposed to would go from the present value to twice as much. It would go from 1% gain through to 2% gain through. You'd be exposed to twice as much UV radiation. In other words, that delicate balance of that layer is very important to life as we know it. And as that layer changes its protective properties, we should be very concerned. And this is one area where special interest groups were not able to deflect the true scientific meaning of this. In the early 1990s, a protocol was established, the Montreal Protocol, where CFCs, carbon fluorocarbon compounds, were banned, which were eating up the ozone layer and allowing this hole to develop. Now those compounds contribute chlorine up to 50 years, so any kind of mitigation of that would have to be done immediately so that we can see a mitigation of this hole hopefully in a 50 to 60 year time, because the chlorine just, once it gets up in the stratosphere, just kind of hangs around for a long time, destroys a whole bunch. It's a catalyst for destroying a whole bunch of ozone molecules. The worst time of the year to compare this is October, when the stratospheric clouds go from their winter state in the Antarctic to their spring state, and they release that chlorine, and we see the ozone hole open up every October. For a while there, it was getting worse and worse. Here's January, when those clouds it's after those clouds have released the ozone, so it's actually not too bad in January. But here was the October just prior to that, and we can see that every day of that October was a mess, as this ozone layer was real thin over the Antarctic continent. Here's the October 2005 average, and supposedly this this square mileage of what this hole covers is getting slightly less. So hopefully we're over the worst part of this effect. Here's 2008. It looks worse to me, but supposedly the hole is getting a little bit smaller. Here's our artistic effect to dramatically show this ozone hole over the Antarctic. Real thin over the Antarctic, probably the cause for an increase in cancers in the Australian continent, which is the closest continent to this ozone depletion. So there's two layers that we have to be concerned about in this delicate balance that we call the Earth. We have a third layer, the magnetosphere. The Earth's magnetosphere is a result of the dynamo effect. In the dynamo effect, the Earth has this iron and nickel and metal type material in its outer core, which is spinning with the Earth, and this spin of this kind of material creates a magnetic field. That magnetic field in turn protects us from charged particles being thrown at us from the sun and from the universe. So if we did not have this magnetosphere, life as we know it would not exist. We need this kind of protection of this magnetosphere for life as we know it. These charged particles from the sun is called the solar wind, and it does tend to change the Earth's magnetic field as it impacts the Earth. It kind of stretches this magnetic field of the Earth out. And recently, in the last year, NASA said that actually our magnetic field is a little bit weaker than we thought it was, but it's still very important in protecting us from these charged particles. Contained in that magnetic field is two belts called the Van Allen belts. They are trapped charged particles that are kind of in a donut shape zones to them around the Earth. In particular, they're not protective because they're just trapped charged particles, but the result of having them is a direct result of having a magnetic field. So the charged particles that are incident on the Earth are being trapped, some of them within these donut-shaped areas. And if you were an astronaut, you wouldn't want to be in those areas because you'd be exposed to greater radiation, greater charged particles like protons moving around. Would not be a good thing. So astronauts try to avoid those. Another consequence of these charged particles being protected by the Earth's magnetic field is the Aurora Borealis, which is a direct result of the deflection of these particles towards the poles. So you have the Australia Borealis in the southern hemisphere, and the Aurora Borealis in the, Aurora Australis in the southern hemisphere, and the Aurora Borealis in the northern hemisphere. And the reason you see these lights is you have these energetic charged particles that are all of a sudden forced to be close to each other. As they come close to each other, they lose some of their energy, which is manifested in light energy. And so you see these different colors of light in the visible range as the energy of these particles are lost as they're forced towards the poles. Here you can see the open bay of the shuttle over here on the left. It's a magnificent effect to see the Aurora Borealis in these colors, and it would be the best thing about living above the Arctic Circle would be to be able to go out at night and see this magnificent display every day. Sometimes when the sun's activity is really high, it can reach further down in latitude, even down into the continental United States. So we have these three layers, very important to the preservation of life as we know it. Earth is also unique in having a hydrosphere. It's the only planet that has a hydrosphere, which is a water layer on its surface. Liquid water will cover 70% of the Earth's surface, and of course that is essential to life as we know it. As we look into the interior of the Earth, we find that it is hot. The interior of the Earth is hot due to radioactivity. So the source of energy that allows the interior of the Earth to be molten and hot is radioactivity. The inner core of the Earth is actually the same temperature as the surface of the Sun, about 6,000 degrees Kelvin. Density of the Earth increases towards the core. This is a direct result of what we call differentiation, as material coalesces and starts to accrete into something. Your denser stuff is towards the middle, and your less dense stuff is towards the outer portions of that object. The six main regions of the Earth, as we go from the solid portion, we have the core, the mantle, and then on top, real thin, up to about 30 miles, is the crust. Continuing outward, we have the hydrosphere, that liquid layer. We have the atmosphere containing the gases, including the ozone layer. And then we have the magnetosphere, which is the magnetic field of the Earth. So those are our six main layers of the Earth: core, mantle, crust, hydrosphere, atmosphere, magnetosphere. As we go into the interior of the Earth, into the core, we have an inner core, which is hot, dense, metallic material under so much pressure as basically what we may say is solid. And the outer core is also dense, iron metallic material, but it's molten. So we have a solid inner core, a molten outer core. And then above that, we have, comprising most of the volume of the Earth, 80% of the Earth's volume, we have the mantle, which consists of dense silicates, basically rock, silicon dioxide. So the element most present in the Earth is oxygen, but in the form of rock, dense silicates. How do we know all this? We haven't really dug into the Earth. We haven't gone more than a mile or two into the Earth, and the crust is 30 miles thick. So how do we know what's in the Earth? Well, you can study the interior of the Earth by seismology. If you had an earthquake, say, there are two kinds of waves given off through the Earth. There are S waves and there are P waves. Seismic waves give us this information. The seismic S waves travel in a transverse direction, like waves on a string. They're traveling up and down as they're propagating forward. So their actual movement locally is up and down. These kind of up and down waves can only travel through solid material. There has to be some kind of reflex action in order to allow this wave to propagate in a forward direction through the surface of the Earth. So all the S goes with solid, surface, transverse direction for S waves. And so you would only see S waves appear where they have traveled consistently through solid material. Hence, when they hit the inner or the outer core of the Earth, which is liquid, that would mitigate any further propagation of S waves. Hence, you could figure out if you had an earthquake and you measure where the S waves appear on the surface of the Earth, you could figure out what is the extent of that outer core of the Earth. There are also P waves, which travel in a longitudinal direction, kind of same direction as they're propagating, and these could travel both through solid and liquid material. So they would travel right through that outer core, but they would be refracted by that liquid, and hence there would still be a zone where you wouldn't get any waves at all. So knowing about the type of refraction that might take place through this liquid, and observing P waves and where S waves end up, you could discern some actual data on the extent of this inner core and the extent of the mantle. There'll be some shadow zone then where both won't show up. Only P waves then would be detected exactly on the other side of the Earth, going both through the outer core and inner core of the Earth. The energy for volcanism as we know it, and what we'll say is plate tectonics, will come from the decay of radioactive elements in the Earth's core. This is the source of energy for all that's happening within the Earth. The result of this is that in the upper mantle you have this sort of liquid type rock called the asthenosphere, where this would also be the source for the volcanic and molten rock that eventually manifests itself on the surface of the Earth. With this molten rock, when it appears, we see such compounds and distributed as carbon dioxide, methane, ammonia, and water vapor. This upper mantle, this asthenosphere, which is kind of like this amorphous molten rock type area, is kind of the basis for what the crust moves on. So the crust is comprised of this rock that can move on this slightly liquid type rock, and hence the crust in these forms of plates move with respect to each other. And we call this whole type of situation plate tectonics. Where these plates meet, there's several possible results. One is that one plate could subduct under another plate. In other words, it would duck underneath another plate, pushing that plate up, and hence you would see mountains at that point. And also, while it's subducting, this first plate is going deeper and might turn it into molten rock, and hence you might see volcanoes on that edge as well. So that would be the ring of fire that exists around the Pacific Ocean, on the coast of the Pacific Ocean, where one plate is subducting under the other plate. Also, you might see trenches at these places, and in fact, if two plates were to subduct together, you might see an enormous trench, as might seen at the Marianas Trench in the eastern Pacific. And so all this would create trenches and molten material. Another possibility as these plates collide is that they slide along each other, and maybe they get stuck for a little bit, and then with enough push, and all of a sudden they'll slip. And when that happens, you get yourself an earthquake and maybe a few other after tremors as it slips from plate to plate. That's what's happening with this kind of sliding action along the coast of California. Or it's possible that these plates are actually separating from each other, as what is happening in the middle of the Atlantic Ocean, where as they separate, molten material is coming up from below and creating new Earth, if you will, at that point. So there's a volcanic mountain ridge through the center of the Atlantic that is constantly creating more and more as these plates. Well, in the past, it was believed that there was one supercontinent called Rodinia. No one really knows what Rodinia looked like, so I've taken poetic license here to create my own image of Rodentia, and so I used a rodent for that. And at one time, this Rodentia had a area to the north called Laurasia, and an area to the south called Gondwana land. And this supercontinent with these two subcontinents broke apart. And again, using my poetic license. I'm imagining what this might look like as these two start to reform into a new landmass. Actually, it wasn't called Rodinia. It was Rodinia. Rodinia. So I just kind of really took a lot of poetic license on that. But it was a supercontinent that broke into it and reformed. And at some point, reformed to make Pangaea, which was another supercontinent just prior to the kind of world that we see now. This world that we see now is comprised of plates on this asthenosphere of the mantle, and we can see the border of these plates where there is volcanic type activity. And you can definitely see how South America and Africa would fit together, or how Africa would fit together with North America, or even how the Asian plate would fit in as well, or Australia into Antarctica at one time. But everything is moving in different directions. You have different things happening at different places on these plates. South America and Africa have spread apart in the last 70 million years. You can look at circumstantial evidence of how they were once together. If you look at biological records, you can find species that only exist, say, on the coast of Brazil and on the coast of Africa, where these two were once connected, but they went extinct at that point. And so you can actually find other circumstantial evidence that proves how these continents were once combined together. Also geological evidence as well. Here's a look at Pangaea breaking up. As this breaks up, you can see North America moving away from South America and Africa. You can see India break off over here, fly up here, and slam into Asia. The result of that is the Himalayas, the highest points on the Earth, the Himalayan mountains, where India slammed into Asia, pushed that rock up, and we have these very high mountains, the Himalayas in Tibet. Another result, as we mentioned, was the California fault, San Andreas fault, where the two plates are sliding across each other, and they may stop for a while and then pick up energy and then finally slip. And when they do, you have an earthquake. That concludes the first lecture in Chapter 5 of the Earth-Moon system.